Here we have the screen from chapter 2. And so last time we introduced the notion of manifolds and semi-Riemannian manifolds. And we had the possibility of having a metric on there. And I'm trying to find exactly or we introduced the notion of the geometry in general, and then we said if you had a semi-Riemannian, or sometimes called pseudo-Riemannian manifold, then you're restricting the geometry to one in which the interval, or generalized distance, if you like, ds squared at the point x in the manifold is always written as a quadratic form. So what's a quadratic form? It's something of this like this equation 2.9, and you see that it's a quadratic form actually in the increment in the coordinates between the 2 points. We're talking about which 2 points? Well, it's the 2 points that we're calculating the distance between, right? One of the points is at x, and the other point is at some coordinates x plus delta x. There's an index here in the superscript, just to remind you, that takes on, for a 4-dimensional manifold, would take on 4 different values for the 4 different possible coordinates. And excuse me just 1 minute, please. Guys, you're talking so loud, it's disturbing my class. Please keep the noise down. Sorry. So the pseudo-Riemannian manifolds have this geometry because it's so very general, because we haven't specified what is the value of this function g, which, notice, it has 2 indices as well, a and b. So in a 4-dimensional space-time, where a could take the values 0, 1, 2, and 3, and b can take the values 0, 1, 2, and 3, you can see we'd have 16 different numbers here in this quantity g. In other words, g can be represented as a square matrix. The signature of that matrix is a key notion. It's the number. Thanks very much. It's the number of positive eigenvalues plus the number. No, I guess I could say it that way. It's just if you assign +1 for a positive eigenvalue and -1 for a negative eigenvalue, and then add up all those eigenvalues, that would give you the signature. Or you just count the number of, another way to say it would be to count the number of positive eigenvalues and subtract the number of negative eigenvalues. For us, we're going to have 1 positive eigenvalue and 3 negative ones. So the signature of our pseudo-Riemannian manifold is -2, and that corresponds to the case of Minkowski space. And that doesn't change in general relativity. It stays the same. Even though the space is curved, the signature of the metric is just this number of eigenvalues that are positive and negative in that way. Remember that the positive eigenvalue is associated with the time coordinate, and the the negative eigenvalues are associated with the spatial coordinates. So really I know this looks a little bit mysterious, but what it corresponds to is the information that everywhere on our manifold, we have 3 space-like coordinates and 1 time-like coordinate. That's the key piece of information that this signature is encoding, and that's all I ask you to know about that. It's kind of obvious, and it's familiar from special relativity, and that generalizes to general relativity. When the space-time is flat, there can be regions in a curved manifold where you have a flat region. Then the interval is still a quadratic form, but it can be written in the familiar one that's familiar from special relativity, and it can be written with this in this form here, where there's a sum over the separate sums for the spatial part and the time-like part. And notice that we introduce the new coordinate x0 represents the t times c. So that's the coordinate x0 that has, even though it's a time coordinate, it has units of distance, just like the spatial coordinates. So from this quadratic form here in equation 210, you can actually read what the metric is. The metric being this matrix of, or represented by, it's actually a tensor, but it's represented by a matrix, so 16 numbers. And you can read off what the, we have another student entering. Welcome, our latest student. And I was just saying that the control was very well done. I was very pleased. Almost everyone did it, and most people did quite well. And by the way, what you've seen is that if you contact me early enough, I'm willing to offer you help and suggestions, and even give you a second chance at resubmitting it with corrections with no penalty, right? That's the point of these things, is to help you learn the material. Okay, continuing with the lecture, if we look at this quadratic form here, we see that there's just a +1 in front of the dx0 squared term. So the g00 is +1. I guess you maybe have to compare this 210, or it would help to compare 210 to this general form here. And we see that the first thing to notice is that there are no cross terms. There's no, like for instance, there's no dx0 times dx3 or dx1 times dx2. That means that the g12 and the g03, they're all 0. In other words, this matrix here is diagonal. And so here, G alpha beta equals 0 when alpha is not equal to beta. That says that the off diagonal terms are 0. And the diagonal terms are either +1 or -1. +1 for the temporal part and -1 for the spatial part, as we see, as you can see immediately in this line here. Okay, so that's how you read that matrix off here. What if you tried to write this equation in a matrix form and you didn't quite get it right? So Please look at your corrections to see the correct way to do it. I didn't remove any points for that, but I just, I have to show you the right way to do it. Excuse me again for 1 minute. Right, where is Carson? You're responsible for him. And keep that door closed. Okay?
Carson, come back here right now.
Sorry, my children are supposed to be going off to school, but
Carson, come here right now. Carson.
Okay. So
Carson,
I'm going to go in the other room so you don't hear my children. Okay, that's better. I guess I wanted to show you how you could write this in the fact that this metric function can change when you change coordinates, even though you haven't changed the geometry. And here's an important example. It's very familiar in that we're just dealing with our manifold. In this case, is the Euclidean plane. So we can't get any more basic, right? Because it's a flat manifold. And and then our ds squared in that case is just a simple Euclidean distance, and according to Pythagorean's theorem, the distance is dx squared plus dy squared. In fact, that's the only geometry the ancient Greeks knew, right? Was the Euclidean geometry, and so that tells you that this that gives you the function for GAB, which we'll cover in a minute. But notice that that function would change if I change to polar coordinates. Then we'd have r squared d theta squared plus r squared. Right, that's how you calculate distances between points. Still in the Euclidean plane, still exactly the same geometry, but we've changed coordinates. So G can change depending on your coordinate, or I guess the proper way to say it is that its representation depends on the coordinates, but it also depends on the geometry itself. So unfortunately, life's a little bit complicated, and we always have to bear that in mind. It's one of the frustrating complications of general relativity is that everything, the things that have physical meaning should not depend on our choice of coordinate system. Distance, for instance, being a quantity that has physical meaning. And yet it's the representation of those things can depend on the choice of coordinate systems. Okay, so here's a little question for you. Well, how would you write the metric for that? You just compare that with the metric or what we did here, and see it implies that these, again, it's a diagonal matrix. It's a two-dimensional matrix because I only have two coordinates, x and y. It's diagonal because I don't see any terms like xy. There's no xy terms. So the g10, or sorry, the g12 equals 0 and the g21 are 0. Furthermore, when we're in the xy coordinates, and the diagonal terms are 1 and 1 because there's just a coefficient 1 here. However, if you write it in polar coordinates, you would have different coefficients. You would have, so we have to make a choice for the order of coordinates. If we say r is the first coordinate, that would be the standard choice. It's not necessary, but it's convention to say r is your first coordinate, theta is your second coordinate. So then the g11 term is 1, and the G12 is still 0 because there's no r theta term. And but now this is interesting. The G22 term corresponds to the theta squared term, and in front of that we have an r squared. So G22 is actually r squared for this Euclidean metric represented in polar coordinates. I'm sure you've seen this before, right? But you probably didn't call it the metric tensor, and you probably didn't call this the line element either. But these are the terms that we use in general relativity because those are the mathematical terms that come from Riemannian geometry and when we have that -2 signature, it's the pseudo-Riemannian geometry. Now, it's always possible to, another complication we have is, I've said that this metric depends on the choice of coordinates. It turns out in order to do this transform from here, I just gave you the metric in both system of coordinate. I gave it to you in Cartesian coordinates, and I gave you the form of the line element here for polar coordinates. But how would you do it in general if I didn't give you the answer? That's a question we're going to take up next later on today. But before I get there, I want to just tell you about a really important fundamental fact that we're going to prove later. And that's that you can always change your coordinates such that the metric, at least locally, looks like the Minkowski metric. So this could be a curved manifold, and we could be in a region near a black hole where we have strong relativistic effects, and yet locally the Minkowski metric could apply. When we say locally, we mean at a point, or more properly at an event. Event is a technical term that means a point in space at a moment in time. But I guess point is a more general term that means just a point in our space, and in our space is a space time, so it's an event. And so this might sound surprising, but you can always choose your coordinates, even in a curved space-time, such that locally, or at a given point, this is true precisely, and in the region of that point, you approximately have that the metric is that of the Minkowski metric. This eta alpha beta is just the Minkowski metric. I think I wrote it down. Well, I won't. It's, you know, the familiar diagonal metric with +1, -1, -1, -1. So this fact is a result that follows from the Einstein's principle of equivalence. It comes from the fact that if you are in a special reference frame, if you're in free fall, for instance, say you're near the surface of the Earth, you climb up a tree, and you're in the space-time near Earth. And so space-time is actually curved. That's because of we know that because of the gravitational field of the Earth is a result of this space-time curvature. and so it's very much real and there. But if you jump out of the tree, you'll be in what's called free fall, en français chute libre, and you would be falling towards the earth. You would be accelerating with respect to the earth, but in your if you put a reference frame which you're the origin, then in that reference frame, that's considered an inertial reference frame, and space space-time around you would look essentially flat if you chose your coordinates correctly. I know that's we're getting way ahead of ourselves in the course, but I just wanted to tell you that probably surprising fact is the basis of the equivalence principle, and the implication is that is that the space-time metric in that special reference frame looks locally like the Minkowski metric. So part of our goal of this course is to, not today, but for the next 3 months, is to explain to you why that is. It's one of the most beautiful results in mathematical physics. When Einstein realized this, he called it his happiest moment of his life when he had that insight, because it let him develop the theory of relativity. He built it up from that idea. Okay, so so you might say, well, hang on, if my metric can always just be written as the Minkowski metric, and when I have the Minkowski metric, I'm in special relativity, I can just use special relativity, and special relativity is easier. Well, why then study general relativity? The point is that the effects of curvature become significant over long distances. Okay, so that's the end of the lecture 2 that I wanted to finish off. And now I want to move on to chapter 3. Ideally, there'd just be 1 lecture for every chapter. So now I'm moving on to chapter 3, which is about the calculus of vectors and tensors on pseudo-Riemannian manifolds. And to study that, I need to introduce some things about how vectors are defined in on a manifold. And I'm sure you're thinking that vectors are very familiar to you, and that's true, but you have a lot of good practice with them, but there are 2 new things you need to learn about vectors. And one of them I'm going to introduce today. It's that, and then the next one will be for next Friday, but the vectors need some care. You need to treat them with care when you're on a curved manifold. Now it's quite going to be some new basic math to you. The nice thing is I can introduce this to you by just considering the globe as a special manifold. The globe is essentially a representation of the Earth as a sphere, right? So it's very familiar, and it's easy to visualize, and so we can use that as a familiar example to help us understand the problem about defining vectors when your space is a curved manifold. So we're going to look at vectors on the sphere. So I'm going to skip this. Well, we just had our resume or summary of the last class, and and I finished off to the last uh, elements of it, that I want to first talk about what's the physical meaning of this interval that we've been talking about, ds. I've called it a generalized distance, but I want to be more explicit about that. And then we're going to move on to the, as I say, the complications of vectors in curved spacetime. Okay, so I'm going to let you read about manifolds and their geometry, the signature of the metric, and this material that we just went through. I guess this, I've added an element here just when I said that maybe I'll say this explicitly now. When I said that your metric locally looks like Minkowski, I can say that more precisely mathematically. I can say it's approximately at one point, you can choose your coordinates, which in relativity means choosing your reference frame too, right? In particular, you choose that free-falling reference frame, and then the right system of coordinates, rectangular coordinates, and then you'll have the Minkowski metric at that point. You'll also have that the gradient of these metric coefficients is 0. This represents the derivative with respect to all 4 coordinates, right? Because the mu index takes on the values, unless otherwise stated, it takes the values 0, 1, 2, and 3 to represent the time and the 3 spatial directions. So we have the time derivative and the 3 spatial derivatives here of this metric, of the matrix that represents the metric tensor. And we're saying that equals to 0 at this point. That is why, that's the precise mathematical statement of what I was saying earlier when I said in a small region around this point, the metric is approximately that of Minkowski. Well, this tells us why. It's exactly equal to Minkowski at the point, and its derivatives are equal to 0. And therefore, if you did a Taylor series approximation, you would only have these second order terms entering in the departure from the Minkowski metric. Now I'm getting a little bit too precise. Sorry. Yeah. Okay. So that's the summary. I'll resist going into any more detail about it. And now I want to really make sure you have a physical understanding of what this ds squared is. We're going to look at it from different points of view. And one point of view is to I've given you, for instance, I started the class today by going back to the Euclidean plane, and then ds squared was just the infinitesimal distance between 2 points. But if our manifold was the flat space-time manifold of Minkowski space, then the ds, if it were extended over a finite interval, it would become the delta s that was familiar from the special relativity class. I guess that was with me last spring, right? When we talked about special relativity, we talked about this interval delta s, and then we had 2 points, A and B, in our space-time, so 2 events, I should say, and and with coordinates, T A, X A, etc. for event A, and similarly for B. And so this, when I say the increments in the coordinates, this is explicitly what I meant, right? It's the delta t is the finite separation in the time coordinates between those 2 events. Delta x is the finite separation in the x coordinate, etc. And and so this was our interval of special relativity. And but remember, there were two distinct cases. In fact, there are three cases you can talk about, but but the third one's a very special one. The first case would be when delta S squared is greater than 0. Even though this is a squared quantity, it can take two different signs. It can be positive when this time interval is big enough, big enough relative to this space interval. And they were allowed to compare them because we multiplied by the speed of light. So this has the same units now. You could just work in units such that time is measured in units such that the speed of light is 1, right? And then we wouldn't see this c squared there. That's the way I'm used to doing it, but we can leave the c squared there just to remind you that that's necessary to have the same units. When the temporal part is bigger than the spatial part in this quadratic form for the interval, this is a reminder from special relativity, right? We said that these events A and B are time-like separated. So in French, du genre temps. So this is something that characterizes their nature, and so we say in English we simply say time-like, and it's time-like because we actually did an exercise in which we showed that when this is true, when ds squared is positive, the time part dominates. So that implies through the Lorentz transformation, we actually, in this exercise, we found the Lorentz transformation such that the spatial part vanished in the new coordinates in the prime. We found the prime reference frame, which was moving inertially relative to the r reference frame here. Such that the spatial part that in the prime reference frame vanished, and so you were left with only a dt prime here. In other words, this ds in that case is simply the proper time. You'd have this formula applying, right? The 3.6 follows from the square root of 3.5, and rearranging, and you find that delta, this dt prime is just the delta tau. Tau is the Greek letter, and this represents a proper time interval. Proper in English and in French here, meaning that you're in the it's the time measured by a clock that's moving with the reference frame. So the sense, I think, is more clear in French because it means that somehow that time belongs to the reference frame. It's not proper in the sense of being, well behaved or correct or something, as it implies in English. The other important case, of course, is that the spatial part here can dominate the temporal part in the interval, in which case delta s squared will be negative. It doesn't mean that delta s is some complex. It doesn't mean that we have to deal with complex numbers, because we never have to deal with delta S itself, because we can just say in this case, well, I'll get to that in a minute. So we give this a different name. We say it's a space-like interval, or du genre espace. And we also showed this in this TD from last year. We found a reference frame in which the temporal interval of or increment vanished. And so then what we do to make sense of this equation and avoid complex numbers is we just multiply both sides by -1, and then we have positive quantities on the left and on the right, right? Correct. So then we can just take the square root, and then this is obviously the distance, or the square root of that is the distance. Square root of -1 of that is the distance, and yeah, and so everything's a real number here, and its physical interpretation is that this is a distance. Okay, so everything I've said in the last few minutes has been about this finite delta S, right? That was, and I did that to return to something familiar from last year and special relativity. But now I want to make the connection with what we're treating this year, which is the ds. And it's simply this, that we've taken if we take the limit of this increment in coordinates. I'm just realizing I should have used a delta here instead of a d for this. I was thinking about the limits already happened. I should have put a delta here. We're taking the limit of these increment in all the coordinates here. Sorry, where was it? We're taking the limit that all four of these increments in coordinates is approaching 0. To succinctly show that I'm taking that limit, I should have had delta x alpha, where alpha, takes on the 0, 1, 2, and 3 for to represent all four coordinates. When that approaches 0, then delta s approaches ds squared, and and so this interval that we're talking about in terms of the geometry of pseudo-Riemannian manifolds, and which is the mathematical structure of our space-time, this ds is simply the limiting form of this special relativity interval that you're familiar with from last year. Okay, that's the material, the main part of the material I wanted to cover from the course notes. I've been teaching this class for several years, and I have a set of course notes that I've tried to improve a tiny bit each year. This year I've decided to do just a major upgrading to write it in the form of a book. My main motivation was teaching this class remotely and giving you, I realized that you really need a table of contents and index and that sort of thing to make these notes more accessible. And I've decided to use this opportunity to upgrade the notes. However, I'm not completely satisfied with my notes for the rest of the class here. And I realized really what I'm trying to do when I'm writing these notes is summarize the material that is very nicely presented by Hobson and others, and maybe, yeah, I think what I'll do is I, I want to stop, I want to switch the screen now. Stop share. Now I want to share the screen. I'm sorry, I'm just trying to figure this out. Oh, darn, I have to, no, why don't I? See, I want to, I want to show the, I'm sorry, I'm not really great with this. See, it's not showing, it's not giving me the new, um, see, I can go to this thing, but I want to share my screen that shows the Hobson book that I sent you. I have the French version and the English version. I hesitated on which version to use, but I think it would be better if I use the English version. Ah, here we go. Okay, finally I can see. So now I'm sharing the screen and we're in this chapter of Hobson's book, and we're in chapter 3, vector calculus on manifolds. Okay, so actually I just want to look to make sure that there's nobody sending me any chats. I'm going to send a little message by the chat, and I'm going to ask if you can see this. Can you see this message? Voila. So if you can see that, please respond. And yes, okay, great. Thanks, Baptiste. And so you have the possibility of responding. So if you have any issues, you can communicate with me during by sending a message to the chat. And I should have done that earlier, shouldn't I? And so, for instance, if you want me to use the French version of this lecture or of this chapter, you can signal that to me. Otherwise, I'm going to use this English version. It doesn't make any difference to me. It's just I'm afraid you're going to sort of casser la tête in trying to make the translation from looking at French and hearing English. And so I'm going to keep my chat window open there and hopefully visible. Not sure how to get it. I have this tiny little screen and yeah, that sort of works if I squish that over here. Okay, so we're in chapter 3, vector calculus on manifolds. I'm going to skip some of this. He's just saying, vectors are familiar, extremely useful, and they're going to be in general relativity, but there's some important considerations that need to be taken into account when we move to manifolds, and it's not at all obvious, and so we've got to work through that. And what and he says that we will, right here, he says we can often consider two-dimensional Riemannian manifolds that can be envisioned as surfaces embedded in three-dimensional Euclidean space. For example, the sphere, which represents the surface of the Earth. And that's, in other words, we're going to use the sphere as our example because it's so familiar. It's and it really has almost all the mathematical properties we need. The only difference is that it's or there are two big differences. It's two-dimensional instead of four-dimensional, and it's a Riemannian manifold instead of a pseudo-Riemannian manifold. So the key thing is the flat version of a two-dimensional manifold is Euclidean space, the Euclidean plane, I should say. And the flat version of a two-dimensional pseudo-Riemannian manifold would be the Minkowski plane, those Minkowski diagrams that you were drawing in your in the the control that we did this week. That's a two-dimensional Minkowski diagram. It represents flat space-time. But those are the only differences. And so in other words, it's very convenient to consider the sphere, and then we can learn all the key mathematical properties, and then it's very easy to generalize it to four-dimensional space-time, and just to mention how the few differences that occur. Okay, so the first point is to consider defining scalar fields on manifolds. I think I'm just going to jump right to the equation here and just say, look, we can define a scalar field. This could be like the temperature on the surface of the Earth. So we'd say we have some function phi, which is it depends on our two coordinates that locate the point on the sphere. And but now the temperature depends on the location, not our arbitrary choice of coordinate system. So if we move to a different set of coordinates, which we're going to represent with an x prime, a would be an index, remember, that takes on two values to give us an x prime 1 and x prime 2, because it's a two-dimensional surface, it's the sphere. And we need a different function, phi prime, of those new coordinates to give us the same temperature at the same point. That's the only sort of familiar, it's a simple familiar point that he's making here, but one worth making because there's sort of profound implications that follow, especially when we move on to vectors and tensors. So now let's move to vectors on manifolds. So a vector field is defined on some region of a manifold M, and it assigns a single vector at each point P in that region of the manifold M. The vector at the point P is often drawn as an extended line segment with its base at P, but this convention requires careful interpretations on manifolds. Once again, it is convenient to illustrate our discussion by considering a two-dimensional manifold such as the spherical surface of the Earth. Let us consider, for example, the vector field defined by the wind velocity at ground level, the wind velocity is measured at a given observation point and refers solely to that point, despite the visual convenience of showing it on a chart as an arrow apparently extending over some long distance. It is an example of a local vector. Other examples include, you can have many examples of vectors. Such vectors are defined at a point P. More accurately, they can be measured by an observer in a laboratory covering a small region of the manifold in the neighborhood of P. Let me just check my mail to make sure it's not one of you, someone, nothing to do with our class. Okay. Of course, the preferred way to contact me now is via chat, but I feel obligated to check the mail. At an arbitrary point P in this manifold, any local vector V lies in the tangent space TP to the manifold at P. I just want to pause here and go back to this chapter and say, look, when he's talking about the vectors are local, what he means is the vector is defined at a point, and if you move to a separate point, then you have a different vector space, and you cannot compare vectors in two different vector spaces. Remember, when you have a vector space, you're allowed to take, by definition, you're allowed to take combinations of those any vectors in that vector space, and that gives you a new vector in the vector space. And that's the defining characteristic of vector spaces, is all linear combinations of vectors in that space give you new vectors in the same space. But that's not, if you consider two different points on the manifold, you're going to have two different vector spaces. He's going to talk about these vector spaces as the tangent space, and there's a good reason that that they're called tangent space, because the space can be visualized as this sort of plane that's tangent to the manifold. I think I can rejoin his text now. I'll start reading the second paragraph, and we'll see how he talks about it. So at an arbitrary point P in the manifold, any local vector V lies in the tangent space TP to the manifold. So think of to have a concrete example, you can think of a sphere, and P would be a point on the sphere, and there's a tangent space, he says, to the manifold at that point. Indeed, TP consists of the set of all local vectors at the point P. In other words, it's the vector space, right? And it's if it's a plane, then it's a two-dimensional space, a two-dimensional vector space. This may be visualized simply for two-dimensional manifolds by embedding them as surfaces in a three-dimensional Euclidean space. Let's look at figure 3.1. So here's his figure 3.1. So here's some manifold, which is a surface in the two-dimensional case. And so we label the manifold with the letter M. And we're considering some point. Here's a point P that exists in the manifold. All the manifold is a whole collection of points, right? So we choose one of those points, P, and then we we visualize a space that's tangent to this manifold at that point. And because it's two-dimensional, well, the tangent space is a plane, a flat two-dimensional manifold that touches this manifold at this single point here, P. And so that in this space TP or plane TP, you can, well, it looks like the Euclidean plane. And so then we're back to familiar territory, and you can define vectors in your familiar way. And in fact, this plane will be, you could think of it as consisting of all the ensemble of all the vectors. But the key thing is those vectors exist at the point P. Let's go back to his description. This may be visualized simply for the two-dimensional manifolds by embedding them as surfaces in three-dimensional space, as in figure 3.1. But the idea is easily extended to higher dimensions and can be defined independently of the embedding space. You don't really need the, so for us, the embedding space here is three-dimensional Euclidean space in which this two-dimensional surface lives. You can, with some effort, just imagine that the only thing that exists is this two-dimensional space. But moreover, at an arbitrary point P, this point P was obviously chosen arbitrarily, local vectors obey all the usual rules of vector algebra in the pseudo-Euclidean geometry. So in other words, once we have this plane, once we're talking about vectors in this plane, so at that point that are defined only at that point P, then we're in familiar territory, and you can comfortably use your rules of vector calculus. But you have to remember that those vectors only are defined at the point P. Now let's go back to his text. It is important to realize, however, that local vectors defined at different points in, say, P and Q in the manifold lie in different tangent spaces. He means that they're in different vector spaces. Thus, there is no way of adding local vectors at different points. Of course, because they're in different vector spaces, right? If we could add them, then they, or take linear combinations, then they'd be in the same space, but they're not. They're in different spaces because they have different tangent planes. I want to pause here and show you my diagram, because what bothered me about his diagram, it's a very nice diagram, but he only shows one point P, and the whole idea here is that this tangent plane is different at a different point. So I want to show you my diagram. So I have to stop sharing. I have to open my figure, and then I have to somehow get to the point where I can, I'm sorry, now I've lost my window that from which I choose the oh, okay. Share screen. Here. Okay. Okay, so now I think you see my figure, right? So this is my attempt to redraw his figure. So I have a manifold M, which is in 2 dimensions, so it's just a surface. I have a point P that's in this manifold, and then tangent to that manifold at the point P, I have a plane because that's the flat version of a 2-dimensional manifold. And in a plane, you can draw, you're back in familiar territory. You can draw vectors. I've drawn 2 basis vectors here, actually E1 and E2, and they exist at this point P and are members of a vector space called TP for tangent plane at, or tangent space at the point P. Now he's saying that if we move to it, he's saying caution, or this is very familiar, but if we move to a different point, let's say point Q, we have a different tangent space. So I wanted to actually draw that for you and show you. Here we're at the point Q, also a point in the same manifold, but because it's separated from point P by a finite distance here, we have a different tangent space. And so this, we can find vectors. I decided to give them different names, F1 and F2. They're just the familiar basis vectors, but the point is these basis vectors span this vector space TQ, which is separate from the tangent space TP. And so I had to indicate that they're different vectors, so I just used a different letter F. But they're just the basis vectors. Okay, so I hope that makes clear now. You can't take it, it has no mathematical meaning to say F1 plus E1. That just doesn't make sense. They're vectors that exist in different vector spaces. Okay. So that was my little improvement, or I guess addition to Hobson's book. I think it's a wonderful book, but I just want to make little additions from time to time. He's also making the point that another thing you lose, here we are back at the same paragraph, but picking up here, other notions that must be abandoned are those of position vectors and displacement vectors, which are clearly not locally defined. Here he has a nice diagram with 2 well-separated points, P and Q in the same manifold, but it doesn't make sense to have a vector that goes from P to Q because this vector at P is in the tangent plane at P, and the point Q has its own separate tangent plane, which is a different vector space. So you can't have a vector from one point to another if they're separated by a finite distance. He does so the notion in short, the powerful message here is that this displacement vector connecting points between P and Q does not lie in the manifold and has no intrinsic geometrical meaning. It just doesn't make sense. He's going to make another point here heuristically, or not mathematically rigorously, but using your physical intuition. However, we can define the displacement vector, a little delta S, between 2 points two nearby points P and Q, since this is a local quantity, or almost a local, or quasi-local quantity. In other words, what he's saying is, let's imagine moving this point Q so it's really close to the point P. Well, then we'd be to a good approximation. The displacement from P to Q is a displacement vector in that tangent plane, and then it makes sense. It's something that lies in this well-defined tangent space at the point P. This is not rigorous mathematics. This is, as he says, heuristic, or trusting your physical intuition. Clearly, if the original manifold is itself pseudo-Euclidean, then the tangent space at any point coincides with the manifold. Thus, vectors defined at different points in the manifold do lie in the same space, and the notions of position and displacement vectors are valid. This reflects our common experience of vector algebra. I guess what he's saying here is that if our manifold was not curved, if it was a flat manifold, then we wouldn't have these problems. Then we could define displacement vectors and position vectors, etc. Okay. Let's move on now to the key concept of a tangent vector to a curve. So this is really how we're going to define vectors in a curved manifold. The most obvious example of a vector field defined on a subregion of a manifold is the tangent vector to a curve, C, which is curly C, if you like, which is defined at each point along curly C. The notion, or the curve, the notion of a tangent vector to a curve is also central to our subsequent development of basis vectors described below. I think I'll stop at the point where I get to the basis vectors, because I want to leave some time for the travaux dirigés. Consider a curve curly C in the n-dimensional manifold. I'm going to say that n is 4 for us. Actually, let's make n 2, so that we're just dealing with a 2-dimensional manifold. This curve may be, just to have a concrete example, this curve may be described by by 2 parametric equations, xa. So here A would take on the values 1 and 2 to indicate that we have 2 coordinates. And these coordinates, x1 and x2, are functions of some parameter u. So u is just a real number, where u is some general parameter that varies along the curve. So we've seen this before in the math class in second year, right? Olivier parameterized curves like the circle using the parameter theta. So u would be theta, and your x would equal cosine theta, and y would equal sine theta. That would be an example of a parametrized curve. And here he's just saying we can do that in a more general way. He's actually doing it in n-dimensional space, and I'm restricting it to 2 dimensions, so it's easier. At any point along P, at any point P along the curve C, the tangent vector T to this curve with respect to the parameter value u is defined as vector T equals the limit of the parameter increment delta u approaching 0 of the ratio of this increment in this interval delta s divided by the increment in the parameter. So delta s is the delta s that we've seen in special what I was referring to earlier as the for us anyways, it's going to be the delta S of special relativity. In our two-dimensional manifold, it would just be a little displacement vector. Let's see how he says it. Delta S is the infinitesimal separation vector between the point P and some neighboring point or nearby point Q along the curve or on the curve corresponding to the parameter value U plus delta U. So I think that's clear. Clearly, so this is how you would define the tangent vector along some curve, for example, in the two-dimensional Euclidean plane, but this can be easily generalized to an n-dimensional space. In fact, it can be generalized to any pseudo-Riemannian manifold, right? Because we know we know the geometrical meaning of delta S, and it just being the interval in that curved space. Clearly, T, it's a vector, right? So it lives in the tangent space at TP, defined at the point P. As illustrated in figure 3.3. So he has a similar diagram to what we've seen before. Again, we have the manifold M, which is just a two-dimensional surface in this simple two-dimensional case. And we've chosen a point P. Again, we have the tangent plane at the point P in which we can have vectors. And now the curve in which C, which lives in the manifold over finite distances, but it's passing through the point P because we chose a point P along the curve, and so the tangent to that curve is a vector that and it will lie in this tangent plane. I think that's intuitive enough. Maybe the only point that needs maybe a little clarification is he says that the tangent vector is with respect to the parameter value U. Now, the tangent vector to that curve always points in this direction, regardless of what parameter you chose to parameterize that curve with. There are different possibilities to parameterize a curve. I gave you an example earlier of, like we saw in the math class, you could parameterize the circle with the angle theta, and but you could have chosen a different angle. You could choose the angle theta divided by 2, right? It'd be a funny choice, but you could do that, and then in order to describe the whole circle, your theta, or let's call it phi equals theta over 2. It's a silly example, but you could do that, and then phi has to go from 0 to 4 pi in order to describe the full circle, right? that would change. Then if you calculated the tangent vector with respect to the parameter phi instead of theta, you would still have a vector that pointed, tangent to the circle everywhere, but its magnitude would change by a factor of 2. So it's sort of a, for us, an irrelevant detail that the tangent vector is with respect to some parameter. You can change parameters and it changes the magnitude of this vector, but not in it's still it just gives you a vector that's parallel to the other one with a different magnitude. And so it's not essential for us at this moment. Okay. So now he's gone through this construction of tangent vectors to a curve. Why is he doing this? He wants you to have a physical picture in your mind about how you can define vectors in a curved space. And that's going to be quite useful when we go back to considering geometry and velocity vectors. And it was why I chose that control. If you've had a chance to look at the control continu partie 2, the part that's due this Sunday, you'll see that it's a lot to do with curves, and that's why I chose that for this week. Anyways, now he has a little paragraph where he's, saying, although the heuristic approach, etc. I'm just going to summarize that by saying he's admitting that we're not doing rigorous math here, even though this might sound like we're doing we are doing more advanced math, but it's not rigorous. And if you really wanted to do this in a completely mathematically rigorous way, you'd have to define the derivative in terms of something called the directional derivative. If you're curious about that, I would encourage you to have a look at the Appendix 3A. I haven't given it to you. You'd have to go to the library and get that book out of the library, or this book out of the library, and look at Chapter 3, the end of the chapter. The end of the chapter, he has an appendix for that chapter that explains the directional derivative and definition of a vector. But this approach we've taken is sort of good enough to have a physical feeling for what we're doing. I want to now define basis vectors. If we're going to deal with vectors, we need, or it's very convenient to have a basis. And how do we define bases? We're going to deal with only one type of basis called the natural bases, or the what Hobson calls the coordinate bases. And we're going to obtain them from the same construction. Actually, they're going to be tangents to curves, but they're going to be tangents to coordinate curves. So I need to explain the notion of coordinate curves to you. And so again, Hobson is just assuming you know what a coordinate curve is. I want to, I've made a little diagram. So I'm sorry, I'm going to get my diagram up in the on my screen, so I can then share my screen with you. So now I'm sharing the little window which is showing coordinate curves. I've made my manifold again, which it's just the surface. It looks more like a blob, but it's a surface in 2 dimensions labeled M for manifold. On that manifold, I have a coordinate system, which I've drawn in a very schematic way. I've said I have 2 coordinates, x1 and x2, because it's a 2-dimensional surface. Of course, this all generalizes very easily to 3 and 4 and higher dimensional spaces. You just need more coordinates. But it's much easier to visualize in 2. So we're sticking to 2. And now I'm going to have 2 sets of coordinate curves. I'm going to have the x1 coordinate curves, which are shown in red. So these red lines are the x1 coordinate curves, and along the x1 coordinate curves, x2 equals a constant. So that's why I wrote this x2 equals constant down here to show that these red lines have x2 equal to a constant. That means, and if we were in a higher dimensional space, x3 would be constant, x4 would be constant. Only, in other words, only x1 is allowed to vary along the x1 coordinate curves. So they're in red here. And then at some point P, again in the manifold, the tangent to that curve is going to be the E1 basis vector. In other words, once we have a coordinate system, just to recap here, we're trying to define these basis vectors, E1 and E2, in our 2-dimensional manifold. So we choose a coordinate system. Once we have a coordinate system, we can define these coordinate curves. Once you have a set of curves, you can define tangent vectors at any given point. You find if you want the basis vectors there, you find the 2 coordinate lines that go through that point, and you hold I'm going to explain now the second basis vector. I'm going to hold the first coordinate constant. So I'm going to hold the x1 constant at its value so x1 is the x1 at the p value here, at the point p. And then that defines this coordinate curve, this x2 coordinate curve that passes through P. And the tangent to that curve then is a tangent vector. And you should ask with respect to what parameter? With respect to the x2 coordinate. So I'm going to use x2 coordinate. It varies along that curve. And it's the only coordinate that varies along that curve by definition. And so I'm just going to choose that as my parameter along that curve. And so of course, I'll take the derivative with respect to that parameter. And that will give me a vector, a tangent vector, which I'm going to label E2. And I'm going to use that as the basis for the second basis vector. I can do that for as many coordinates as I have. So I'm going to have the same number of basis vectors as I do coordinates, which is the number of the dimension of the space. In other words, that's going to span our manifold, or sorry, that spans the vector space with its tangent to the manifold at any given point in the manifold. Now I think I've gone back to sharing this. Yes, the sharing the screen where Hobson is going to explain all this. I hope I can. Well, I'm going to try and go through this quickly since I've given you a little background on it. So basis vectors, As we have seen, a vector field on a manifold is defined simply by giving, in a smooth manner, a prescription for the local vector. So local meaning it's only defined at a given point, but we do that for every point. A local vector v, which is a function of x, the coordinates of the point, at each point in the manifold. At each point P, the vector lies in a tangent space, TP, at that point. This vector is a geometrical entity. That means it's defined independently of any coordinate system with which we choose to label the points in the manifold. Nevertheless, at each point P, we can define a set of basis vectors EA. A is just an index here, even though it's down below. There's a reason for that. It's just an index that takes on the number of values that's the dimension of our space. So for us, it's going to be, A is going to be 0, 1, 2, and 3 for the time and 3 space coordinates. So we're going to have 3 basis vectors in, or sorry, 4 basis vectors in 4-dimensional space-time. And these basis vectors are a basis for the tangent space TP. So the tangent space at the point P. The number of such vectors being equal to the dimension of TP and hence of M, just as I explained. How this may be achieved will be discussed shortly. Well, in fact, I just explained it to you. Any vector at P can then be expressed as a linear combination of these basis vectors. Well, that's what we mean by basis, right? Provided that they are linearly independent. Well, that's a necessary condition to be a basis, which we will assume always to be the case. Thus, we can express the local vector field V at the coordinate, or at point with coordinates x, at each point in terms of basis vectors E sub A. And now notice the basis vectors are a function of the point in the space. That's why we put, the basis vectors, read this as being a function of position in the space defined at each point. So V, the vectors at the point X, are some VA, so these are just real numbers that, and there's 4 of them in a 4-dimensional space because the index A takes on 4 different values, 0, 1, 2, and 3. And those components, these are the components of the vector, right? And they're the components are a function of position and multiplied by the basis vectors. There's the component times the relevant basis vector. In other words, the A has to be the same as, the index here is the same as the index there. And these basis vectors in turn are functions of the space. They have to be, right? Because the tangent, the vector spaces themselves change with position in the manifold. Now, remember this convention of Einstein. So whenever you have a repeated index, one upstairs, one downstairs, in the same term, you have to implicitly it's implied that you have to sum over that index. And now I've just explained, if you like, why they put that index downstairs on the basis vector, because the index went upstairs in the component of the vector. Okay, so in a sense, this is very familiar. We're just saying that a vector is a linear combination of the basis vectors. The notation is new. The summation convention of Einstein is new. And the fact that the really new thing for you is that these basis vectors are changing with position in the manifold. That's the really new thing that I've introduced to you today. Okay. The numbers VA of functions of X are known as the contravariant components of the vector field V in the basis EA. Now, why are they introducing the notation contravariant components? Well, it turns out that vectors come in different types. There are two types, actually, contravariant and covariant. And so he needs to distinguish these contravariant vectors from covariant vectors. We are going to learn about this, not to, we're going to learn about covariant vectors next week. I want to save that for next week. Let's just stick with covariant, contravariant this week. Okay, so it's enough already that we've introduced this tangent space and the vectors as tangents to curves and existing and tangent planes that are tangent to our vector or tangent to our manifold and the vector spaces depending on location. Those are the new points for today. We'll deal with covariant next week. Any set of basis vectors. Okay, so he's going to get into the dual basis that we're going to deal with next week. Let's skip that. Let's skip over all of that. Coordinate basis vectors. I'm going to leave this for you to read on your own. It's just that he's just going to explain what I just explained to you just now, and he's going to make the connection with the metric tensor, which is really quite beautiful. And then he's going to talk about changing bases. Raising and lowering, we'll deal with that next week. That's converting between covariant and contravariant components. To really understand these basis vectors, we need to understand how you can relate them in different coordinate systems. And it really follows just from vector calculus that you can show that if you change coordinates to another coordinate from the old coordinate system XA to a new coordinate system X prime A, then you'll have a new set of basis vectors, right? Because the tangent the coordinate curves will be different, and so the tangents to those coordinate curves will be different. But there'll be vectors in the same vector space because they're all applying at the point P, and so there can be written as linear combinations of each other. And this and what's the matrix that relates the two? Well, it's just the Jacobian of the transformation, as indicated in this equation 3.9, and he proves that to you. And I want to stop with this for now, because I'm supposed to be helping you with the control for this week, right? I've given you a control continue partie 2, which I would like you to hand in on before midnight on Sunday. And the sooner you get it into me, the better for you, because then I'll try my best to look at it. I do have my children this weekend, but I'll try my best to look at it and I'll even I'll even give you pointers to improve it. So right, so this is due Sunday, and so we I wanted to relate these things we're learning about parameterized curves and tangent vectors to just familiar examples from even from classical mechanics and Galilean kinematics. So we come back to classical mechanics, and we consider a point particle that is moving in the Euclidean plane. So the Euclidean plane is a manifold, but it's we didn't normally think of it that way. It's just a flat Riemannian manifold, and our particle, it follows a path or a trajectory with the coordinates that are given x and y in our coordinate system, but those coordinates are functions of time or some parameter t, which we interpret as the time coordinate. And here I'm just saying that there's no distinction between proper time and coordinate time, because we're in classical mechanics. And I'm assuming that these functions x of t and y of t have some smoothness properties that let me take the derivative. They're continuous, obviously, and even differentiable, or at least one-time differentiable. So which means I can define the velocity at each point along the curve. So at the time t equals 0, the particle is located at point P, and at another instant, it's t at the parameter value t equals 1, it's at the point Q. And I want you to write a general expression for the infinitesimal distance squared. So let's write that as dl all squared along the trajectory at an instant t, and write it as a function of the intervals of the coordinates x and y. And I'm giving you 0 points for that because I wanted to just work through this with you, because I wanted you to be able to focus your attention on the new material. So so it's I hope it's clear. I gave it to you in the lecture, right? Because this is we're in classical mechanics. So the only space known back in those classical days was Euclidean space. So you use a Euclidean geometry, and in particular Pythagorean's theorem, and dl squared is dx squared plus dy squared. So, right. So the exercise really is I know you know Pythagorean's theorem. It's really, we're just getting used to this sort of vocabulary and this way of thinking about parametrizing curves and finding distances in our space, etc. So we're going to now exercise 2, write a new general expression. Write a general expression for the distance, infinitesimal distance dl along the trajectory as a function of yeah, so now I want just dl, not dl squared, and also I want it as a function of the interval of time dt. Now this is a little less obvious, but just what I want you to do here, maybe some of you got it, but divide, so we've got dl squared is dx squared plus dy squared, right? Now just divide both sides by some increment in dt all squared. So on the left-hand side, I'd have dl squared divided by dt squared. On the right-hand side, I'm going to have dx squared divided by dt squared plus dy squared divided by dt squared. And then write those as dt by dx all squared plus dt dy all squared. So that, but then recognize that as the x component of the velocity squared and the y component of the velocity squared, right? It's just dt dx all squared plus dt dy all squared. And now take the square root of both sides so that we have on the left-hand side, we'd have dl divided, take the positive square root. So dl divided by dt equals the square root of the sum of this two velocity components. Now bring the dt from the denominator on the left to the numerator on the right. So then you would have dl equals square root of, if you like, vx or dt dx all squared plus dy dt all squared. And in both those terms, the sum of those terms are under a square root sign, and that whole thing is multiplied by dt. So it's a function now of this interval dt. I hope that was clear. If not, please send me an email and I'll try and make that more clear. Okay, now write a general expression for the distance between 2 points P and Q using your previous result. Well, this is what we did in Olivier's class, in the math class, right? We found distances. We always had a specific curve in mind, but you could just write it in the general way. It's as an integral, right? We integrated along a parameterized curve. So you would integrate dl along the curve to get the total length equals, that's on the left, just integrating the previous expression. On the right-hand side, it would be the integral of this square root of, or under the square root sign, you'd have, if you like, it's vx squared plus vy squared, or x dot squared plus y dot squared, however you want to write the two velocity components, both under the square root sign, times dt, and you're integrating that from the time, or from the coordinate time at P to the coordinate time at Q. So from TP to TQ, if you like. Okay. Now that was all in Cartesian coordinates. Now I want you to repeat the thing using polar coordinates. And as we saw at the first part of the lecture today, when you're considering dl in polar coordinates, you have a metric tensor that intervenes. There's an r squared times d theta squared plus dr squared, that equals dl squared in polar coordinates. It's still Euclidean geometry. It's just you've chosen Euclidean, polar coordinates. Okay. And now I guess I just wanted to, well, now we're getting into the part of the control that you're supposed to do, for half a point for each of these exercises. And I guess I've made the curve a concrete example now, just to keep it simple. We've got a circle here, and we're going to test those formulas that we've just went through together, right? We're going to use our previous results in polar coordinates to find the distance between the distance along the curve traveled from time t equals 1 to t, or t equals 0 to t equals 1. So if you just look at here, r is staying constant and theta is going from 0 to 2 pi. So it's done a full circle, hasn't it, in that time interval. And so we should get the circumference of a circle, which you know from your geometry classes, it's 2 pi times the radius of the circle. But I don't want you to just write down that result. I want you to as I say, use the formula here that you got and apply it to this case. So please show your work, then verify. Next question: verify your results. Your earlier results in Cartesian coordinates. Even though Cartesian coordinates in general are easier, they're more complicated here. And but you should get the same result. Now that I think about this, it's been a while since I've done this, but I'm thinking it through, and I'm realizing you're going to have to break the trajectory. The trajectory is a circle, right? It's a complete circle. But to do this in Cartesian coordinates, you're going to break that circle into two half circles, right? It's going to do a semicircle in the when y is positive, and then it's going to do a semicircle when y is negative. And remember, you took a square root. You're going to have to take the negative. I'm thinking a bit intuitively here. I can't see all the steps immediately in my head, but I can see that you're going to have to break that circle into two parts, and it's probably going to involve something about you're taking a square root, and you have to make a choice of the sign of the square root, and you're going to have to make two different choices in order to get the full circle. I hope that's strong enough of a hint here to help you with that. Break your circle into two half circles. I think that's true. Maybe I better do that myself, and I'll but don't hesitate to ask me questions if you get stuck on that. Or even if you just want to verify. Or the best thing to do is do this early and then send it in, and I'll if there's time, you can redo it if it's not right. Okay, next question. The coordinates, the best coordinates for a problem depend, of course, on the problem. So if we had, for instance, a straight line between the points P and Q, you could write them in Cartesian coordinates in this way, right? I think we saw that in the math class. You can always write Cartesian, you can parameterize a straight line in Cartesian coordinates in this way between, in general, two arbitrary points P and Q in the Euclidean plane. And now try and just to make this point that the best coordinates depend on your the problem at hand. Clearly, the polar coordinates were best for the circle, but when we're dealing with a straight line, if you try and write this straight line in polar coordinates, you're going to find it's complicated. So I'd like you to have a go at writing the equation for the straight line in polar coordinates. It's surprisingly not straightforward, but the point of this exercise is not to frustrate you, but to show you that, to really emphasize that your choice of coordinates is important. And then I want you to write the general expression for the distance, the infinitesimal distance dl along a straight line as a function of the as a function of dt. But I'm just asking you to write the general expression. I'm not asking you to do any integrals. Don't evaluate the integral. Your general expression, I can tell you, will involve an integral, but you don't have to evaluate the integral. So don't go crazy or don't get frustrated trying to do a complicated integral, but it's enough to write down the expression for the integral. I see that's the time we had for today. So I'm going to leave you with that. I just want to say two things before you all sign off on me. So please read through those handouts, either in French or in English, the Hobson's book for next day. And then we'll continue that presentation. And the next week, we are going to cover the what's called the covariant components, or also what he calls the dual basis. The material that I was skipping over today, we're going to cover that next day. But first of all, you want to, of course, finish this second part of the control continu due this Sunday. Don't hesitate to ask me questions. I really do want to help you. It's not cheating to discuss it with me. Is for, in my point of view, as long as you're learning the material, that's the main point of this control, is to get you to learn the material. So please don't hesitate. You can talk to each other as well if that helps to discuss it with your friends. But finally, when you write it up, you have to write it up yourself so that you really understand and learn the material. And I think you all did quite a good job. I'm impressed. I got 7 out of 8 controls. Or 8 out of 9 handed in. So that's really good. Please keep up the good work. And I'll see you next Friday. See you then. Bye now.